Welcome back to the latest lecture session. We were looking at suspended solid removal, and we know that gravity is our friend, but we want to help gravity to see to it that our job is done faster. So what are we trying to do? We are trying to destabilize the stable system such that smaller particles come together and then they settle down. So destabilization, coagulation, and then bigger particles being formed after the initial coalescence, flocculation, right? So we are going to discuss the aspects related to coagulation. We looked at two primary variables. One is theta, how much time, and how much mixing. So let's look at the typical values. So it depends on the type of coagulation you want. One is sweep coagulation. So here theta is 1 to 10 seconds, relatively higher compared to the other ones we are going to look at. And level of mixing, you can see that mean velocity gradient. It's G equal to dV by dz, that's what we know, right. So it's 6 to 1000 per second, right, relatively longer times, and still high enough mixing but not very high, because you want to have precipitation also being formed, let's say, right, and adsorption taking place. So now you can compare that with respect to the adsorption coagulation, where charge neutralization and maybe initial interparticle bridging is of greater relevance, or charge neutralization primarily. So here we see that the theta is much lesser. In the earlier case it was 1 to 10 seconds, and G is also much higher. Earlier case it was 6 to 1000, 600 to 1000, here it's 3000 to 5000. So much more intense mixing and relatively lesser time, let's say, right. But in general we are concerned with G theta. It's not that this is a same value, even though G theta for this adsorption coagulation might be comparable to the sweep flock coagulation. We also need to be concerned about G and theta, the independent variables too, right, because that will also have an effect on the kind of mechanism and how effectively is it going through. So that's something to keep in mind. Let's go through. So here we have a problem. Using the info which will be provided, we want to use or select an inline blender where we are adding coagulant. And what's the data? We are going to use the data from the previous case, and for that case I think the pH was 6 in the last session, and also something like 12.5 milligram per liter or such, but it should be presented in the succeeding slides. And flow rate is given, and water temperature, yes, is also a relevant aspect. And here we are saying that its adsorption and destabilization is the predominant mechanism, not the sweep flock coagulation. So that's what we want to have. Inline blender, this is what we have, and you have different dimensions and such, yes. So again, let's go about and look at it. So we know that we want to get our relevant G and theta values, right. So that's at the end of the day, that's what we are concerned with. So from here I have different dimensions and such. I have the motor power given, so you can choose one motor, let's say, as a trial. Initial one will be trial, obviously. And from the jar test data from the previous or 2 sessions before, pH is 6, optimum dose, flow rate is what we have now, and we know that for destabilization or charge neutralization based adsorption and destabilization, we know that theta is less and G is relatively higher. And the temperature, why is it relevant? Because the viscosity of water changes with temperature. So this is the temperature from the this is the temperature, this is the viscosity at that particular temperature. So this is what we have. So let's go ahead and look at it. So trial, we are selecting something here, and looks like the dimensions are C and D inside the chamber. So now we can calculate the chamber, let's say chamber volume, pi d square by 4 h pi r square h, and we get the relevant volume, let's see, right. Let's look at the this thing once, C and D. So this is the volume of the effective volume of your particular system, let's say, right. So that we got from the table. And then the retention time, how will you calculate the retention time? We know that we have Q. So theta is equal to V by Q, and that's what we have. You can play around with the units, and it's 0.5 seconds. We know for what we want, 0.5 seconds is what we want. So it's more or less fine, right. And what next? G, we need to look at G. Here we are assuming that not all the energy from the 1500 watt rated motor power is going to be transferred to the water. We are assuming that the efficiency is around 80%, let us say. So, effective P is 0.8 times 1500 watts. Again, these kinds of things will be from experience and such. If not, at least in the homework or exam, this will be given. So, we know that I think G was equal to square root of power by mu into V, if I am not wrong, right? You can correct this variable. So, that is what we have, square root of P by mu, right? And what else is this? V is volume, I guess, right? Let me just check that. Okay, no need to check, that is what we have, volume out here, right? And from that we will get the G value, and G value is this will give us an idea about the mixing. So, in this is acceptable. I think we were looking at 3000 to 5000 for our particular case. So, this is acceptable from that point of view, right. So, we looked at, or we are more or less done with coagulation. So, once I am done with coagulation, provide enough intensity of mixing and enough time for the particles to be destabilized. What do I want to do? I do not want to continue that further. Why? If I continue that further, the flocks or these colloids are not going to come together. So, we are going to look at flocculation. So, to take a holistic view, so initially we have a repulsive ion cloud, right, electrical double layer. This is what we have. After adding coagulants, we destabilize them, and I guess again different ways. So, we repulsive layer is neutralized by the coagulant and particles are destabilized, right, they are destabilized. Obviously, theta was 1 to 2 seconds or 0.5 to 10 seconds, let us say. So, it is order of few seconds, that is what we have here. And then we want the flocks to come together. If we still hold very high G values or very high intensity of mixing, the particles are not going to come together. So, here you want to give greater retention time, obviously typically 30 minutes or such, and then you will have particles aggregating together and flocks being formed. So, coagulation and then flocculation, right. So, that is what we have out here. So, let us move on. So, what is our goal? Obviously, we want to convert or see to it that the smaller particles aggregate and form bigger flocks. That is what we have. How does it come about? As in, now these particles have to come close together, right? How is it now? Now they are not anymore stable. They do not have that repulsive layer or relatively less thick repulsive layer, but now they still need to come together. So, what are the different ways? We looked at one figure earlier wherein energy transfer from large eddies to smaller eddies and then to the micro scale. It is similar. So, micro scale, perikinetic, macro scale, orthokinetic and differential settling, let us say, right. So, these are the three mechanisms by which different particles can come in contact. Micro scale. So, Brownian motion, let us say diffusion relevant aspects. So, again Brownian motion, this is due to the thermal energy of small particles. We are talking about very small particles, 1 micron, let us say, almost virus size, I guess. So, important, not virus size, relatively higher than virus size. It is obviously important for very small particles, right. Again, it is caused by Brownian motion. So, macro scale, this is based on the fluid flow, right, macro scale, bigger or not bigger, macro scale. So, it is obviously for bigger particles and we want to use it to promote agglomeration too, right. And differential settling, different particles have different settling velocities. I think we looked at it in sedimentation and such, and then they can come in contact. And also when we have different fluid velocities being imparted to the water, again these differential settling velocities will also play a role, let us say, right. So, differential settling, macro and micro scale mixing, let us say. So, that is one aspect to consider. And different ways of flocculation mixing. Earlier we looked at inline static mixers and such, but here you are going to have relatively bigger systems at play. Why is it that we have bigger systems at play? It is because you know that the retention time is not in the order of a few seconds. Now, it is in the order of a few minutes or even half an hour, sometimes even 1 hour. So, obviously, if for the same flow rate, if the water has to spend more time, right, you need a bigger volume. Theta is equal to V by Q, right. Theta is equal to V by Q. If theta increases, V also has to increase. So, cubical shape, typically cubical shape where we have the vertical turbine, this is the vertical turbine, with the drive motor and such. Impeller located at a depth equal to 2/3 of the water depth, 2/3 of the water depth, 2/3, right. So 2/3 of the water depth. So gentle, what do we say, flow of water coming in, and then you are going to have gentle mixing out here, yes, and then it's going out to the sedimentation basin. Here we are trying to form the flocks here, vertical turbine. Then you can have the paddle flocculators. You can see now that this is the side view, right. Even earlier I guess it was the side view, and here you have the paddle flocculators. So by rotating in this way, and you know that different velocities, because velocity of this what do we say, paddle here will be lesser than the velocity of this paddle here. So you are going to have differential velocities being imparted to the fluid, and then you are going to have mixing, let's say, right. Again, water coming in, water channels, so that there is less short circuiting and also gentle flow of water coming in, and perforated baffle wall, again to create the ideal flow conditions, so that again to prevent short circuiting in general, and then it goes to the sedimentation basin. So if I cut it at this section and look at it this way, so this is what a paddle looks like, right. I am looking at it from this way. So it's mounted, and you have the drive and you have the paddles. So you need to be able to design these, as in what is the width of this, what is the distance between two paddles, how many paddles and such, because that will lead to this energy from the motor, or the power from this motor being transferred via the paddles into the water. So that's why you need to be able to design these aspects. What else? Okay, other than that, you also have baffle channel or hydraulic flocculation. So you just have baffles, right, water taking the flow, and then relevant mixing, let's say. So here it's also over and under, water comes in, this is the level, and due to the head it's going to go over and under, right. So different kinds of flocculators. So horizontal shaft, vertical shaft, and hydraulic flocculation, what are the advantages and such. Let's look at what are the primary aspects of concern. In general, we are concerned with type of flock, how much is the head loss. If the head loss is too much, obviously again initially I need to pump the water to a higher head. So I don't want that to be high, right. So operational flexibility, what is the initial cost and relevant aspect. In general, you see that horizontal shaft with paddles is best or pretty good, and vertical one so-so, and hydraulic flocculation also pretty fine, but there is head loss though. So these are the aspects you will need to consider when you try to balance between your requirements, I guess, right. So again, highest energy input potential, I guess, you can impart a lot of energy with respect to this vertical shaft, so you have greater control, looks like. We will not go into it in detail though. So primary design variables, again, what is it I am concerned with? I am concerned with imparting enough energy, right, through the motors and then the paddles or the hydraulic flocculation chambers, such that there is enough turbulence but not a lot, such that the flocks come together or flocks are formed, right. And here obviously theta is a primary aspect. Earlier in coagulation it was the order of a few seconds, and here we know that it's in the order of a few minutes. And as you can see here, G values are remarkably less. Earlier we were looking at ranges from 600 to I think 5000 G values, right. Here though you can see that the values are, or the level of mixing is relatively less. We are still going to have mixing, but it's not at all rapid. If I have or continue with this level of mixing, what's going to happen? All the particles are going to what do we say, break up, or the flocks are going to break up. Let's move on. So types of mixing based on paddles, as we saw, can be horizontal or based on a vertical shaft. So what is of concern? How is it that the energy transfer will take place? So here it's friction force. This is coefficient of drag, area and such. Let's see what we have. Velocity of the paddle with respect to water, right, and area of the paddle, velocity of the paddle, area of the paddle, and coefficient of drag, which will be depend upon length to weight ratio, not weight, length to width ratio, let's see, right. So that's something you can get from the relevant tables. This will be the friction force. How will I be able to what is that, get power? It will be force into velocity, as we looked earlier, and the velocity of the paddle. So force into velocity, So that's what we have. Earlier we had square and now we have cube here, right? And if there are different blades or such, you are going to sum them up, sum power consumption over all blades. So per blade, if this is the consumption, what is the consumption over all the blades, you will just sum them up. So velocity of paddle looks like we need to be aware of one aspect, as in earlier we saw this, if this is the shaft and this is the paddle holder, these are the paddles, right? So obviously velocity here relatively less, higher, right? It's going to rotate in this direction, let's say, and look at the distance being taken by this, look at the distance being taken by this, and look at the distance being taken by this, all within the same time. So the velocity obviously is different. That's what I think we are trying to say here. So application of paddle flocculator requires our understanding or consideration that velocity of paddle with respect to the water is not the same as paddle with respect to fixed coordinates, right? That's one thing to keep in mind. Why? Here, what is Vp? It's the velocity of paddle with respect to water, not with respect to fixed coordinates. That's something to keep in mind. And that velocity varies with distance from axis, right? And as you can see, it varies from distance from axis, let's say. Velocity of paddle with respect to water depends on velocity of paddle with respect to fixed coordinates and now obviously velocity of water. That's what we are trying to see. So what does it depend upon? This is the ratio of velocity of paddle with respect to water to velocity of paddle with respect to fixed coordinates, right? So again, we are taking into consideration both the fixed coordinates and also the velocity of water, let's say, right? Typically 0.75 and 2 pi r is the perimeter, let's say, right? And n is rotational speed, as in rotations per time. So this is the distance and this is rotation speed, let's say, right? Or this will give me units of what now? Rotations per time, okay, distance per time. So that's what it gives me an idea about. So typically K value is 0.75, velocity of paddle seems to be that this is the range out here, right? So let's move on, and I guess this is a good figure. You can see the paddles, right? You can see the paddles and water is flowing in this direction, horizontal shaft, and you have the relevant paddles. You can observe the spacing. There are different spacings you need to be aware of. This spacing between the wall and here, between the floor and the lowest point of it, and also this spacing, and then spacing between the paddles and also the width of the paddles and I guess the length of the paddles. So these are the dimensions that you have to be aware of when you design it. Let's see how we will design it, but again, this is how paddle flocculator looks like, let's see, right? Okay, so here we see that there are 3 boards per arm, as I mentioned, the distance between the boards, right? Okay, paddle I guess is the term that encompasses all this setup, and then the width and the length. These are the aspects we are going to look at. So this is going to go over and above and over and above. That's how it's going to keep mixing. So at the end though, close up of flocculator paddle wheel in the last chamber, at the end when the water is about to exit. To reduce the G in the last compartment, there are now only 2 instead of the usual 3. And in general, you are going to have multiple compartments, as in it's not going to be only one compartment with uniform level of mixing. So initially relatively higher G may be 50 and then maybe 30 and then maybe 15. So this is how it's going to go. So that's why here they are saying that in the last compartment they have less close up, what is this, to reduce the G, 2 arms, that's the term I was using or thinking of. So they have only 2 arms rather than 3 arms. Why? They want to decrease the G, right? So that's something to keep in mind. As you can see here, the area plays a role, area of the paddle. So if you decrease the area, right, you are going to decrease this power, right? So that's how, and again you know that power is proportional to the G value, right? G is square root of P by mu volume, right? So if you decrease the power, you can do that different ways. So you can decrease the area, let's see. That's what they were trying to do in that particular context. So in general, you have the recommendations. Again, if this is asked in the exam, this will be given. If it's asked in the homework, you can look this up, I guess, right? G, we know that it's what, 20 to 50 per second. That's what we have. So, different relevant aspects, depth should be 1 meter greater than the wheel diameter. So, we know that this is the wheel, so the depth should be greater than 1 meter, let us say, or total depth should be 1 meter greater than the wheel diameter. And again, clearance between the wheels and walls, right. So, if we have the clearance, so this clearance is a relevant issue, right. And wheel typical diameter is 3 to 4 meters, spacing between wheels on the same shaft, as in, so we have different wheels, this is one wheel and this is one wheel. So, we need to have some spacing between wheels, let us say, right, and that is what they were talking about there, spacing between the wheels on the same shaft, rims on adjacent shafts, okay, and paddle width, typical length, typical width obviously centimeter, right, this is what, and typical length 2 to 3.5 meters, yes, and area of paddles per tank cross section, number per arm usually 3, spacing is usually given at 1/3 points on the arm, but it can vary. So, 1/3 I guess if this is the total, right. So, that is what they are saying, 1/3 on the arm, right, and length by width and such. Okay. So, these are the general aspects which we will look at when we try to design it, right. So, let us look at the other aspects too. Turbines, they use power number like the mixing basins. Baffled channels, we already looked at it, end around or over and under, right. This will create the gentle mixing conditions. Baffled channels, so you have channel velocity, right, power, and again depending on head loss you can equate them. This is something we already looked at for the static mixers, I believe, when we looked at the power dissipation. So, from that you can equate the level of mixing to the head loss and the retention time, right. So, that is something that you can get. So, how do we get this head loss or such? We have the Manning's equation for open channel flow, or from this formula, let us see, right, where for head loss in square pipe going around 180 degrees turn, right, 180 degrees I guess, right. So, 180 degrees turn. So, that is the relevant aspect. So, you can have that formula, let us see. So, G depends on velocity of flow through the plant, okay, this is one aspect to keep in mind. So, it is difficult to operate well at a different plant flows. For hydraulic or these baffled channels, the issue is that G depends upon the velocity of flow through the plant. So, if it is varying a lot, obviously G will vary a lot. So, you can't control it very much if the flow is varying too. So, that is something to keep in mind. So, you have to maintain a very narrow range of velocity, especially when you are looking at these baffled kinds of what do we say, baffled channels and such, right. So, that is something to keep in mind. So, 3 flocculator basins, so you can see them, 1 here, 2 and 3, right. These are baffled type, I guess, not baffled, I think, okay, these are not baffled type, both baffled and I guess with respect to the horizontal shaft mixing, right. So, baffled channels, let us see, the flocculator basins are arranged to operate in parallel, right, all 3 are parallel, they are baffled for end and around. They are going to end and around. Flow will enter through the circular holes at the top of the picture and exit through the rectangular windows to sedimentation basin at the bottom of the picture. Okay, you can see this flow is coming through here, water will come this way, right, end and around, and then it will exit here, right. This is I guess only for baffled. I thought they were also going to have the shafts here looking at these particular holes, but maybe I was mistaken, let us see, right. Interior of flocculation basin showing opening for paddle wheel drive, right. So, paddle wheel drive shaft, okay, this is what. So, you have the opening for the paddle wheel drive shaft, right. So, okay, baffled walls flow through holes, typically the percentage of holes is such that 3 to 6% of wall is open holes, and velocity is relatively less, 0.3 meters per second at the opening. We do not want to exceed it. For example, initially area is this and now it is coming through a particular relatively less area, then velocity can increase if you do not design it well. But the issue is if velocity increases, then you are going to have flock breakup. That is what it is that people are referring to here, right. So, types of mixing and other design considerations. Trade-off, okay, if you look at G theta, again this is for your relevant case of flocculation. So, you can go from one end to the other, tapered G for optimal conditions, this is what we mentioned. So, initially high and then slow and slower, let's say, or lower and lower, let's say. You can have multiple basins and such, or you can have combinations that will allow for common wall and then transport to sedimentation, let's say, right. So that's something to keep in mind. So we are going to look at the paddle flocculator design, but this will take some time, and I already looked at all the or consumed all the time I wanted to for this session, but let's just look at the question once. We want to design a paddle flocculator, and how do we do that, or what do we need? We need the basin dimensions, the paddle configuration, how much power is required for that paddle, the rotational speed for the following, and the rotational speed for the following parameters. What is given? Q is given, and they already gave us the theta. So from that, obviously I can calculate the volume, right. And they don't want only one compartment, they want 3 compartments, let's say, right. And water temperature is given. For that, the dynamic viscosity is given, and coefficient of drag is also given. This depends on length to width, let's say, right. So this is what we have. So what are we designing before? Okay, this is what we are designing. So water is coming in through here. This is the top view, the plan, right. So here G is 40, or was it 50? Okay, what's the G? G is 40, 30 and 20. So 40 relatively more mixing, lesser mixing, and much lesser intensity, and that's how it's going out. And here in the side view, this is what it looks like, let's say. So I want to be able to get the dimensions and this clearances, the depths and such, let's say. And also I'll have to look at the spacing, but spacing we already know that it's at 1/3 along the arm. That's what we have. I need the width and the length of these arms, right. So this is what we are going to design, but for that, what am I going to use? I know that theta equal to V by Q. I can calculate V. I can calculate the level of mixing required. I know that it is 40 per second to the power that's required, volume which I already have, and the dynamic viscosity which I already have. So I already have the power. Power I can use and put it up here and plug it in here, let's say. This is the power, right. And once I get the power, I'll have this. I already have coefficient of drag, I have rho, and then area I will get that. Vp2 I'll be able to calculate and then design accordingly. So these are the primary equations we are going to use, but this I'll continue in the next session. Thank you.